I'm Ariah Klages-Mundt, and today I'll talk about optimal intervention in economic networks using influence maximization methods. This is joint work with my advisor, Andreea Minca at Cornell. To motivate, complex systems come with complex risks. In this case, we're interested in the cascading effect of shocks to the economic system. To try to combat these cascades, governments can deploy intervention tools that try to support the value in a shocked economy. This includes the stimulus following the 2008 financial crisis, such as government financing and monetary policy, and today new tools are being proposed to combat the current crisis. The goal with intervention here is something like maximizing the overall value in the system subject to a budget constraint. To further motivate, let's compare these two crises. So in the financial crisis, there was a shock that originated within the financial system. In this case, the intervention target is relatively simpler because it's systemically important financial institutions. Whereas in the COVID-19 crisis, the shock is external and there are really disruptions to many different economic sectors across the world. In this case, the intervention is much wider and harder to target. Now, there's a rich background on interventions. For instance, it's well known that network effects underpin systemic importance in loss cascades. There's also been a lot of work on the form of optimal interventions, like looking at capital requirements to control for aggregate risk, and the form of optimal capital and liquidity interventions, in this case targeting core periphery banking systems with methods that apply to small systems. There's also been work on intervention problem in the Eisenberg-No model, where the problem can be formulated as a mixed integer linear program with a certain notion of an epsilon optimal approximation. I like to think of economic network analysis as two layers of a stack. In the first layer, we need models that are realistic and with understood uncertainty. And given this, in the second layer, we can apply these models. This includes computations that we can do and insights that we can get. This second layer is the focus of this paper. So in particular, we abstract from the details of intervention and focus on the computational aspects. With large systems and widespread shocks, these problems quickly become computationally hard, and we're in need of approximations that can scale a network size. We use the economic network model from Elliott, Golub, and Jackson. In this model, there are random valued assets and nodes which own assets as well as parts of other nodes. And the node value here is normally a linear function of assets and connected nodes. Now, if a node value falls below some threshold, there's a nonlinear default cost that's incurred. And the rationale here is that businesses have buffers to absorb some level of losses. And these default costs propagate through the cross-holdings to other nodes in the network, which may trigger a cascade of other defaults. Formally, the model can be described in terms of asset prices and asset ownership, a matrix C that describes the node cross-holdings, as well as the outside ownership of each node, and then also the node failure thresholds and node failure costs. Given this, the model is described by this equation for market values. And it's important to note that there's this scaled relationship involving the cross-holdings that describes the interconnection of the underlying assets and any nonlinear failure costs that are triggered. The optimal intervention problem then becomes find an intervention payments vector gamma subject to budget B, where gamma changes the threshold activations as follows. Here we want to maximize a weighted function of the nodes saved subject to this budget constraint, and the intervention is effectively lowering the failure threshold of the receiving nodes and affecting the resulting cascade. Our results extend the literature on influence maximization from Kempe et al., Mossel and Roche, and Domain et al., and extends it to the setting of economic networks. I'll give a quick overview here of the main ideas. So the influence maximization problem is composed of a node set U, an influence function f that describes the influence exerted by a set S, and a weight function w that gives the importance of nodes. And then again we have the activation thresholds and a budget. And the idea is that we want to find an initial seed or activation set S0 and then iteratively construct the activated sets according to how the influence propagates. So for instance, with this graph, we may start with the seed set S0, and that propagates influence that activates the set S1, which then in turn activates S2. And then the problem really becomes to find this initial seed set S0 that maximizes the weight of the total activation subject to the budget constraint. And there are two main takeaway results here. One is that this problem becomes computationally hard, and that a modified form of the problem is actually submodular and admits a 63% approximation. Shifting back to our economic intervention problem, our first result is that optimal intervention is NP hard and hard to approximate. Formally, for L less than alpha, if alpha n nodes initially fail, then it's NP hard to determine whether there's an intervention gamma subject to the budget, such that at most Ln nodes fail post the intervention. Now the proof idea is that a simple bipartite form of the problem reduces to independent set. This draws on an analogous result from Domain et al. Done for the linear influence model in influence maximization. But it deviates in that it involves a more complicated triggering model, which we have to handle with additional steps. In particular, the influence matrix becomes a Neumann series, which includes, importantly, self-loops, and the form of the influence function and the influence thresholds becomes a bit more complicated. Our second result is that a reframed version of the problem is well approximated, here by randomizing thresholds and now optimizing in expectation. Now the problem becomes a submodular problem for which there is a hill climbing algorithm with a 63% approximation. Formally, this is that if thresholds are independently distributed such that the composition of the distribution function and the influence function is increasing submodular, and in addition, if we have that the weight function is monotone and submodular, then it turns out that the expected objective function is also monotone and submodular, which allows us to use the submodular approximations. And the proof idea here is that we have to show the conditions in Mossel and Charmet. And these conditions are actually quite broad. So for instance, the uniform distribution works, and the range of the distribution can basically be arbitrarily small. This leads to a case where actually having a little bit of uncertainty makes the problem easier to solve, which is akin to a smoothed analysis idea. Basically, the problem is a lot easier except on a set of measure 0. We also have a third result where basically it's the same situation for identifying the worst case failure scenarios that can happen. So in particular, it's NP hard to identify these worst case cascades. But similarly to before, we can apply the 63% approximation to actually sample large cascade events with some guarantees. And this actually suggests that this could be a good importance sampling method. Another consequence that we show in the paper is that calculating expected node values can be computationally complex because of this reason. So formally, this is that if asset prices evolve from some P0 to P1, such that the change is less than some max aggregate shock B, then it turns out it's NP hard to determine if there's a cascade of size L that can happen. We then want to test out these ideas with real networks. So we use the World Input-Output database. This data set essentially maps the flow of resources between different economic sectors in different nations. So the data set includes 43 different nations and about 2,500 distinct sectors. And starting with this data set, we then construct realistic looking models that's consistent with this data and study shocks in the resulting models. We then handle the intervention problem in these scenarios using the methods that we've explored. So the greedy algorithm with guarantees actually involves very large Monte Carlos for a large dimensional system, and so is simply too slow to use for this purpose. But drawing from influence maximization literature again, there are heuristic algorithms that are efficient and basically close enough to the greedy algorithm. And so we use those to demonstrate a proof of concept simulation. I'll briefly walk you through the results of this proof of concept. We simulate 5,000 shock scenarios and apply the approximate intervention algorithms and explore the effectiveness of a range of budgets. The results are represented in the 2D histogram here. And the y-axis is the percent of firms defaulting in a run, and the x-axis is the budget size. The grayscale is representing the histogram, in 2D histogram, and the colored lines are contours representing the topography. Now you can think of a traditional 1D histogram as a vertical slice of this image, and so here's two such slices from the right and left sides of the 2D histogram, representing the budget's 0 and 1% of total assets. And notice here a large reduction in the tail mass from intervention, as we would hope. Now we can draw a parallel from the contour lines in the 2D histogram to this next chart, which plots the tail values at risk versus the intervention budget. So here the axes are the same as back in the 2D histogram. And the tail value at risk measure is telling you, given that you're in the qth quantile of worst scenarios, what is the expected loss, or in this case, the expected percent of firms defaulting? And there are a few main takeaways here, mostly dealing with the gradient of the image. And so with relatively small budget sizes, the approximation algorithms give us actually pretty large reductions in tail risks. So there's a bit of low-hanging fruit here. And then we also see a quickly decreasing return to scale in the size of the budget. And it's worth noting here that the 1% of total assets is actually on a reasonable scale with the size of actual interventions. To summarize the paper, we've constructed efficient approximations of optimal economic intervention that builds on influence maximization. And it also allows the efficient sampling of large cascade events. Note a caveat though. This assumes that we start from models with well understood uncertainty. This is really a separate problem of tuning a model and verifying accuracy given the data that's available. And this is the earlier step really in the stack that I described before. We can't really expect miraculous outputs in practice without this. So on a realistic level, this provides a new computable tool toward designing interventions and stress testing, but there's still more to the story. And finally, I'd like to thank the NSF and Bloomberg Fellowship for supporting this work.